Hey everybody, Dr. Retzik here with you. This is our fourth and final video in section 7D and also our final video of the entire quarter here in Math 406. Let's get started. So last time we introduced the idea of singular values, and we had this example where t is a linear operator on F3, and it's got this formula: t of xyz is z 2x 3y. Okay, so you feed this thing x comma y comma z, it spits back out z comma 2x comma 3y. All right, and now what we found was, since the matrix for t star t turned out to be 4, 9, 1 on the diagonal, which is not surprising because t star t is a positive self-adjoint operator, we can simply read off. We read off the singular values of t. It's S1 equals 2, S2 equals 3, and S3 equals 1. So every time, all you have to do is just read off the positive square roots of whatever's on the diagonal of the matrix for t star t. Those are your singular values. Alternatively, these are the eigenvalues of the unique positive square root of t star t. So these are the eigenvalues. Eigenvalues of root t star t. For that radical notation there for the square root, it's just pixels on a screen, and that symbol stands for the unique positive square root of the positive operator t star t. Okay, so we have these things called singular values. Now, these are eigenvalues of root t star t, not of t itself. In fact, this t only has one eigenvalue with a one-dimensional eigenspace. So it's not exactly t that we're looking at, but at the same time, t is definitely an isometry times root t star t. And in that sense, t is really similar to the operator root t star t. I mean, it's only off by an isometry. Now, that isometry can definitely scramble things up after root t star t is done with them, but not that badly, which leads to the last idea of the quarter. Let's take any vector v in F3. So we know nothing about the vector v. If you do t to that v, you're doing t to some linear combination of the orthonormal basis of eigenvectors for root t star t. Remember, root t star t has a diagonal matrix with its eigenvalues down the diagonal. So there's a basis of eigenvectors for root t star t. Say those eigenvectors are e1, e2, e3. Okay. In our example, it's the standard basis, but in general, there will be some basis. And since that basis is orthonormal, if you want the linear combination of them that equals this input vector v, well, from chapter 6, we know you just do v inner product the first one times the first one plus v inner product the second one times the second one plus v inner product the third one times the third one. If this were a more abstract discussion, we would have a linear combination in those parentheses of E1 through En. Here, in our example, it's three-dimensional. Okay, but remember, T, by polar decomposition, is an isometry times root T star T. So that's really what's acting on this linear combination. Now imagine that root T star T hitting each of these terms as it works its way through the parentheses. Don't forget that each of those inner products is just some number, and that each of the vectors E is an eigenvalue of root T star T. Eigenvector of root T star T. So really we have S acting on, okay, now the root T star T passes through the parentheses and we get V E1 inner product, and then when the root T star T hits this, what happens? Well, we get that first singular value times E1. Similarly, when it hits the next term, we just get the next singular value times E2. And finally, when it hits that last term, we pick up that last singular value times E3. Okay, now S has to act on each of those terms. Pass S through the parentheses, hit each term, let the constants, the scalars on those vectors E1, E2, E3, pass through S since S is linear, and we get here. We get S1, inner product VE1, SE1, plus S2, inner product VE2, SE2, plus S3, V inner product E3, SE3. Now, S is an isometry. So since E1, E2, E3 is an orthonormal basis, those orange underlined vectors are an orthonormal basis, and we can rename them singular value S1, V inner product E1, all times vector F1. So F1 is just a symbol that stands for S of E1. Wherever S sends E1, call it F1. Plus S2, V, E2, F2, plus S3, inner product VE3, F3. So what you have here is a way of expressing T acting on V in terms of the singular values and two distinct orthonormal bases. There's the original one, E1, E2, E3, which plays a role in all those inner products. And then there's this new one, SE1, SE2, SE3, which is the actual vectors whose linear combination makes T acting on V. If you prefer the matrix notation version of things, I think this is really telling. In terms of matrices, if you were interested in the matrix for T with respect to E1 through E3 on the domain side of the picture and F1 through F3 on the range side of the picture, which is unusual for operators. Normally, when we try to write down the matrix for an operator, we think of the basis on the domain side of the picture and the range side of the picture as matching, but you don't have to. You could form a matrix by asking, all right, let's see where E1 goes, but let's express it in terms of the Fs. Let's see where E2 goes. Let's express it in terms of the Fs. Let's see where E3 goes. Let's express it in terms of the Fs. And if you do that, look at this line here. If V happened to be E1, then that's 0, and that's 0, and that's 1. And so the combination of the Fs that produces T of E1 is just S1 of F1, zeros everywhere else. If V happened to be E2, then only that middle term of the purple underline would survive. And if V happened to be E3, only that third term would survive. And that visual is very strong. You could read this as, oh, okay. So every operator, literally every operator, has a diagonal matrix representation with respect to two orthonormal bases, E1 through En, F1 through Fn. They don't match. We're not willing to call the operator T diagonalizable, but still, if you're willing to use two separate orthonormal bases, one on the domain side of the picture, one on the range side of the picture, then literally any operator has a diagonal matrix representation. And it's a direct consequence of polar decomposition and involves these magical numbers called the singular values. And that's it. So in that sense, literally every operator is nice. Maybe you have to route it through a couple of distinct orthonormal bases to make it look nice, but every operator is nice. Every operator has this polar decomposition. Now there's structure, because you know so much about isometries and positive operators. So that's it. You guys have studied this quarter inner product spaces, the structure of inner product spaces, all the geometry that you have access to there that you didn't in an arbitrary vector space, thanks to the inner product and subsequent norm. And then you studied operators. on inner product spaces. And so we have this big classification of all these different types of operators, and in the end, any operator at all is relatively simple. Isometry times positive square root. It's been a pleasure. Good luck. Come to class with questions. I'll see you next time.